the University of Wyoming, they had 10,000 students and they had 14 bars. There was a Thanksgiving. We always used to have a Thanksgiving blizzard, and nobody could get out of town. They'd all get stuck. And there was one particularly fierce blizzard that we had, and the liquor stores actually sold out of booze. It was so funny. You couldn't get anything but what nobody wanted. I mean, they had plenty of bottles of sake, but everything else was gone. Okay, so we're back to rudimentary subatomic physics. I'm going to review a little bit some of what we went over on Friday, and then move ahead. We were looking at atoms and elements, and we found that atoms aren't indivisible. They have smaller particles within them, and even those particles can be subdivided, but then the physics gets really weird. We have protons, neutrons in the nucleus. The nucleus of the atom is therefore positively charged, and it's exactly balanced by an equal number of electrons. So the number of protons and the number of electrons match in a neutral atom. The electrons are sort of massless. They have a very tiny mass, and so you can sort of ignore them. And they're, in a sense, sort of spinning outside the nucleus of the atom, although spinning is really not the exact term that you'd want to use. Again, take physics if you're sort of interested in that. So we had some examples to look at, and really what you can think of is the electrons being in a cloud outside of the nucleus. They're in specific locations, as we'll see a little bit later. But here at the first part of this figure, we're looking at a helium atom. It has 2 protons, 2 neutrons. So its atomic mass, the protons plus the neutrons, is 4, because each one of those weighs 1 atomic unit. The electrons are on the outside, and they exactly balance the protons, so you have 2 electrons in a helium atom. A carbon atom would have 6 protons, 6 neutrons, and 6 electrons. So its atomic mass would be 12. The electrons and protons balance. And we're not actually showing the electrons there. We're just showing a cloud where those electrons would be expected to be found. And then there's a little bit of physics there that tells you why we don't sort of think of the electrons as whizzing around the nucleus. They don't have angular momentum, and the other thing that sort of confounds us is that we can measure the velocity or the location of one of these particles. We can't measure both. Heisenberg uncertainty principle tells us that. So the result is we just sort of think of those as whizzing around on the outside of the nucleus. But they're in specific locations, as we'll see. All right, isotopes. Isotopes of elements are atoms that differ in the number of neutrons. Okay? If you change the number of protons, you change the element. The properties change. Okay? And so since we have a difference in mass, those isotopes must contain a different number of neutrons. And I gave you several simple examples. Hydrogen has 1 proton, no neutrons, 1 electron to balance the proton. Right? That's what most of the hydrogen that you find will be like. But there's a significant amount of hydrogen that is actually deuterium. It contains a neutron. It's still hydrogen because it has the same number of protons. Still has much the same properties as hydrogen, but it's heavier.
So why isn't the mass of the neutron counted unless it's in the isotopes?
Well, it is counted. For example, a carbon atom has 6 protons and 6 neutrons, so its atomic mass is 12. Okay? And we're doing the same thing here. Hydrogen has 1 proton, no neutrons. Its atomic mass is 1. A deuterium isotope, its mass would be 2.
Gotcha.
Okay. Good. Okay, and then tritium has 1 proton and 2 neutrons, and that's unstable. That doesn't like to stick around. So the result is it gives up energy and mass. That's one of the definitions of radioactivity. But tritium is an isotope of hydrogen because it has 1 proton. Okay, so here's some isotopes of carbon. Carbon-12, carbon-13, and carbon-14. Carbon-13 is very unstable. It doesn't stick around long. Carbon-14 sticks around a little bit longer. In a sample of carbon-14, for example, you'd expect half of it to have broken down into carbon-12 in, what is it, 5,700 and some odd years. Okay, so it sticks around a while. Carbon-14 is always being regenerated in the atmosphere. So we always have a certain amount of carbon-14 in us. We also have a certain amount of tritium. We have a certain amount of radioactive examples of other elements, radioactive nitrogen, radioactive oxygen. Right? So your bodies are radiating all the time. And it's, you know, you probably think you live a healthy life by eating organic food and staying away from nuclear power plants. Unfortunately, your body contains radioactive isotopes, so you can't get away from it. Your bodies are radiating all the time. It's not a high level, but it's there. Right? How do we know carbon-12 has 6 protons and 6 neutrons? Well, I knew that because I knew the atomic mass. But how do you find the atomic mass? To do that, we use the periodic table of elements. If you've taken chemistry, then you've seen the periodic table. There are 2 examples on either side of the room of periodic charts of the elements. We'll be using these a lot in the next week or 2 to define the properties of elements. Okay? The periodic table organizes these elements by their properties. Okay? So if you look at the periodic table, over here, for example, okay, each column of elements has similar properties. Okay? There will be just some differences from element to element, but many of the properties will be the same. Hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, all of these are going to have pretty much the same properties and do pretty much the same chemical reactions that all of the members of that column will do. Okay? The atom size and mass increases as you go down the column. So hydrogen is the smallest of the atoms in that column, and francium, number 87, is the biggest. And just by virtue of the fact that it has a lot more neutrons and protons in the nucleus. And that size is going to matter as far as the chemical properties are concerned. All the numbers that you see up on that periodic table are meaningful. Right? And you're going to be able to use that periodic table to figure out the properties of the various elements that we have to deal with. Okay, so let's look at an example. Right? Here's an example. You can actually find this element on that table. You just look for number 77 up there. Okay, so it's right up sort of in the middle of the table. All right, so we have 3 numbers that we're concerned with. That top number is the atomic number. The element symbol, each element has a 1 or 2 letter symbol. Okay, that's in the middle. And then at the bottom is the atomic mass. Okay, this is element number 77. It's iridium. It's a naturally occurring but rare metal. There's not a whole lot of it. And these are its properties. Okay, so what do those numbers mean? Well, the atomic number is the number of protons. Right? So elements in the periodic table are arranged by the number of protons they have. Okay? Or they're arranged by the number of protons. So if you look up at this atomic or this periodic table and you look at number 3, lithium, for example, element 3, that 3 tells you there's 3 protons in the nucleus. Okay? Any atom that has 3 protons is going to be lithium. It's going to have lithium's properties. Right? But you can change the number of neutrons and therefore change the mass. Right? So if you change the number of protons or the atomic number, you change the element. The atomic mass is the total mass of the atom. And since we can pretty much ignore the electrons, this is just the protons plus the neutrons. Okay? Why is it fractional? Well, it's because a certain percentage of iridium atoms that you come across are going to be isotopes, and they're going to have differing numbers of neutrons. Right? But for our purposes, we don't have to worry too much about that. We can just round this off to 192. All right? So then we're still begging the question of how many neutrons? Well, it's easy to figure out. Now that you've got the atomic mass and the atomic number. Okay, well, iridium is element 77, so it has 77 protons. All right, that's simple enough. The atomic number is the number of protons. If you have a neutral atom, which most of the atoms we deal with are going to be neutral, at least for now, it has a matched set of protons and electrons. The charges exactly balance. The result of that is that you have the same number of electrons as you have of protons. Okay? So it must have 77 electrons. Piece of cake. All right, how many neutrons? Excuse me. You subtract the atomic number from the atomic mass. Right? If atomic mass is number of neutrons plus protons, subtract the number of protons, you're left with the number of neutrons. Simple algebra. All right, so 192 is the atomic mass. You subtract 77, that's, I started counting on my fingers at that point, 115. Okay. I actually do that with a calculator. I don't trust myself to add 2 plus 2 without a calculator, and it still comes out to 5 sometimes. I don't know why. I was never very good at math. Right? So an iridium atom should have 115 neutrons. A typical iridium atom. Some will have more or less because they're isotopes. But they're rarer. Okay, well, let's see if you understand this. We have a neutral atom of lead. The symbol is Pb. That comes from the old Latin term for lead, plumbum. Okay. Contains how many protons, neutrons, and electrons? So take a little bit of time and see if you can figure that out using the periodic table. Okay. You can consult with your neighbors if you want to. Okay, so let's take a look at this and see if we can figure it out. The first step in solving a question like this is to look up at the periodic table and ask yourself which element is this symbol referring to. Okay, what number is it? And if we look up at the table, we see that lead is number 82. Right, that instantly tells you how many protons there are. Right, 82 protons. So we can eliminate two of these answers right off the bat. We can eliminate C. We can eliminate E because they start out with 125. So we're left with 3 additional answers. Right, we know pretty much that the neutrons are typically not going to match the protons except in the smaller elements. You can demonstrate that by looking at the atomic mass. The mass of lead is 207.2. Well, you just round off to 207. So you subtract 82, the number of protons, from the atomic mass, 207. You're left with 125. Okay? Since you know that the number of electrons exactly balances the number of protons in a neutral atom, you know that it must have 82 electrons as well. So of those answers, B must be the correct answer. Okay? 82 protons, 82 electrons, 207 minus 82 is 125 neutrons. All right? Very simple. All right, I guarantee that you'll see some questions like this on the exam, so you need to know how to do this. It is fairly easy to do. Okay, just don't confuse those numbers. Sometimes I'll see people confuse the atomic mass and the atomic number, and they'll think the atomic mass is the number of protons. It's not.
So the order is protons, neutrons, and electrons.
In this question it is, yes. I said protons, neutrons, electrons. Okay? If I said protons, electrons, neutrons, right, then it would have been 82, 82, 125. Yeah. Right, so that's just an issue with reading the question. You'll have to look at the order in which these are presented and make sure that you follow that same order. Right. Okay, any questions on this so far? Pretty straightforward. Okay. Okay, I promised that the electrons are in specific locations outside the nucleus. And so we need to take a look at that, because that is going to be one of the major properties that determines how atoms interact with each other. Right? The location of electrons is all important. Right? They're not all just out there wherever. They're in specific energy levels. Okay. The mass of the nucleus plays a little bit of a role, but it's a lesser role. It sort of determines at what rate these atoms will interact with each other. The smaller ones interact with each other faster and more readily than the heavier ones do. Okay. So the electrons are arranged according to the amount of energy they carry. Okay, so the lowest energy ones are closest to the nucleus, and as you go up in the amount of energy they carry, okay, you get farther and farther and farther away from the nucleus of the atom. Right, so lowest energy closest to the nucleus, highest energy farthest from the nucleus. And so we actually arrange these electrons in these energy levels, okay, which are called shells. Right, so we have different numbered shells, shell 1, shell 2, shell 3, et cetera, et cetera. Right, they're subdivided into orbitals. Okay, and each orbital can hold 2 electrons. But the shells can hold different numbers of electrons. All right, so what are the rules for filling these shells with electrons? Right, the lowest shell, shell 1, can hold 2 electrons. That's it, period. End of statement. Okay, so the first 2 electrons that you're trying to fill around the nucleus, they go into shell 1, because you always go from lowest energy to highest energy. Okay. The reason for that is the stability of the atom. You can pop an electron up to a higher shell by giving it more energy. But that's not stable. If there's an open space in a lower shell, it's going to pop back down to that lower shell. All right, so the lowest shell holds at most 2 electrons. That's where the first 2 go in. If you run out of space there, then you have to put them in shell 2. Shell 2 can hold 8 electrons. Okay. Now here's another important rule. When you're adding electrons to shell 2, you keep them unpaired until you have filled up 4 spaces. Okay, then you start pairing electrons up. And I'll show you some examples of how this works. All right, so keep them all unpaired until 4 are added. All right, the next shell holds 18. But all we have to worry about is the first 8, because we're not going to go any farther than that. Most of the atoms that are required or that we look at a lot for living systems are smaller elements. And especially carbon, nitrogen, oxygen, hydrogen. So those are the ones we're going to need to work with the most. Right? So the rules for the third shell are exactly the same as the second shell. Okay? And if you have to add more electrons than that, then you've gone too far for this class and you don't need to bother. Okay? Take chemistry if you want to do that. Well, many of you will probably end up taking chemistry anyway. Okay? I used to talk about orbital shapes and electron numbers in those orbitals, and I don't bother anymore. It's pointless. Again, take chemistry or physics if you really are curious about that. These 3 rules are all we're going to need. Okay? All right, some examples. Okay, hopefully everybody can see this. If you can't, let me know, because then I can just move it over to the other screen, but I think it should be okay. So what we want to do is we're going to look at some examples of electron configurations. Okay? Can you all in the back read that, or do I need to write it a little bit bigger? Is that okay? Okay, good. This illustrates a third reason why it's really good to use PowerPoint, because my writing is almost illegible. I often have people telling me, what is that letter? So, all right, simple electron configurations. Let's look at hydrogen. Okay? Baby simple. I'm going to represent the nucleus with the atomic symbol because I don't want to draw out all the protons and neutrons and that kind of stuff. And I'll just draw the shells outside. It's got 1 electron. So what we need to do is we need to just put that electron in, and bingo, we're done. Right? That's all you can do. If we wanted to look at helium, which is the next element up, okay, symbol is He. It has 2 electrons. And a helium atom, then we have the lone electron there. We need to put another electron in, so we pair it. Okay, so that's shell 1. This was electron 1, and this was the next electron I put in. Okay. Let's look at lithium. Okay. It's got 3 electrons. With lithium, the first thing we do is put in that first electron. We then pair it up, so there's electrons 1, electron 2. Problem is we have another electron we have to put in. That one is going to go up into the next shell. We've already filled shell 1 with as many electrons as we can put in there. So now we have to go to the next shell. So we draw another shell out here. We'd put an electron in, and that would be number 3. And we're done. Okay? The next one, beryllium. The symbol is Be. It's got 4 electrons. And your first instinct may be to put 2 electrons in there and then put 2 electrons in like that. Nope, exactly. You don't pair them up until you've got 4 spaces filled up in this second shell. So instead what we have to do is we have to say, well, beryllium must be like this. It's got shell 1, 2 electrons, and then shell 2, it's got 1 here and another one over here. Now why do I go clockwise? I don't know. Just because I do. I mean, you go counterclockwise and it doesn't matter. Okay. I guess I go clockwise because I think conventionally. Yes?
The atomic number tells you also how many electrons are in the atom?
Good question. Does the atomic number tell you how many electrons there are? Exactly right. Because the atomic number is the number of protons, and in a neutral atom, the number of protons and electrons match.
Are they all
right?
neutral?
We are assuming that they are all neutral unless we're told that they're otherwise. There will be situations a little bit later where we will be dealing with non-neutral atoms, but you'll be told that they are, or you'll know that that's what's going to happen, okay, because of the properties. Okay? So when we're filling in these electrons like this, we're going to be assuming that we're starting out with neutral atoms. Okay, good question. Thank you. Okay, we go to number 5, boron. Okay? Symbol is B. It's got 5 electrons. So we have the first 2, 3, 4, 5, and we have an open spot over here for an unpaired electron. We go to carbon. Has 6 electrons. So we have the first 2, 3, 4, 5, 6. All right? That's as far as we can go with unpaired electrons in that second shell. What we're going to have to do now is we're going to have to start pairing those up. So nitrogen with 7 electrons, yes, nitrogen, 7 electrons. Okay? What we do then is we have shell 1 filled, shell 2, 3, 4, 5, 6. Now we're going to have to start pairing them up. Again, I just go clockwise. I start at the top again and go around clockwise. You don't have to. You can put that electron in anywhere as long as you pair it. Okay? Oxygen. 8 electrons. So oxygen is going to have 2 in the lower shell, 3, 4, 5, 6. Then we start pairing 7 and 8. Okay? So there's nitrogen and oxygen. The next one is fluorine. Okay? Fluorine is a nasty, nasty gas. You've heard about fluoride, of course, in toothpaste. Well, that's a non-neutral form of fluorine. Okay? Neutral fluorine gas is nasty. It burns. If you inhale it, it'll burn your respiratory tract because it reacts very violently with it. It'll get into your bloodstream and replace all the calcium in your bones with fluorine. It's just nasty, nasty stuff. And it has 9 electrons. Okay? So fluorine then, we'd have 2 there, 3, 4, 5, 6, 7, 8. 1 unpaired slot for fluorine. Okay? And then finally, one more example. We go to neon. We have 10 electrons. And neon then is going to have 2, 3, 4, 5, 6, 7, 8, 9, 10. It's nice and filled up. Okay? Now, if we were to go to the next one, number 11, sodium. Again, that symbol is from the Latin term for sodium because it was known to the Romans. It's called natrium, is what the symbol refers to, but we call it sodium. If you were to go to sodium, you've got 1 extra electron, and you're sort of stuck because you've already filled up shell 1 and 2. Simple problem. You just go up to shell 3 and start filling that. Okay? So then sodium with 11 electrons is going to have, I should have written this out, sodium, is going to have the 2 there, 9, 10 there, and we finally have to go up to shell 3, put a lone electron in, okay, all by itself. Okay? So then as you went across that next row to magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, you're going to basically be doing the same thing you did before, filling in shell 3 this time instead of shell 2. Okay? That's as far as we'll go. We won't mess with potassium and calcium because then we have to start doing funny things with shell 3 and we don't want to mess with it. Okay? Any questions on that? Make sense? Okay, good. All right, so we've followed our rules for filling shells. You've seen how to fill those shells and put the electrons in the correct locations. Here's basically what we did. We have the electron configuration for the big 4 elements of life: hydrogen, carbon, nitrogen, oxygen. Okay? Notice how the electrons are being placed in the shells. We have, for hydrogen, on the left part of this figure, there's one electron, there's an open space for another electron to go into shell 1. For carbon, we filled shell 1. We have 4 open spaces in shell 2. Nitrogen, we start filling in the pairs, so we have 3 open slots. Oxygen with 2 open slots. Fluorine with 1 open spot. And neon with none at all. Okay? So there are the electron configurations. The number of unpaired electrons is critically important in understanding how these atoms are going to interact with each other. All right, that's one big issue. The other big issue is how many electrons are in the outermost shell. That's going to tell you also how they're going to interact with each other. Okay, so 2 big issues there. And what we're talking about here are chemical bonds. Okay, attachments or connections between atoms. All right, so atoms combine to form molecules. Remember, molecules are groups of atoms. We haven't really said how they're grouped. How is it that they're holding together? Is it because of charges? Is it because of something else? Well, it turns out it's because of these chemical bonds that are forming between atoms. That's what holds molecules together in specific ways. Okay? How do you think about the bonds that are going to be formed? Right, as I said, there's 2 major issues here. The number of unpaired electrons in the outermost orbital, outermost shell, okay, and the size of the atom, okay, and also where it is in the periodic table. But that really is a factor or function of how many electrons it's got. All right, so it really boils down to 2 things: the electron configuration and the size of the atom. And that's going to determine what kinds of bonds it forms. Okay. We're going to look at basically 2 bond types that we can talk about, and actually a subtype of the covalent bond. It'll be a polar covalent bond. The ionic bond and the covalent bond. All right. Those are the 2 major types of bonds that we need to deal with. Okay, let's talk about the ionic bond first and look at what ions are. Okay, now there was your question earlier was, are we always going to assume that an atom is neutral? Okay, not necessarily so. Sometimes atoms are charged. Right? They can't lose the protons, right? Unless you're dealing with radioactivity or you've sort of smashed atoms against each other and popped some of those protons out. If you change the number of protons, you've changed the element. Okay? So since we're not changing the element, a charged sodium atom is still basically a sodium. Right? We haven't changed the protons. What we're changing is the electrons. Okay, we're losing or gaining electrons to change the charge of the atom. Okay, so that's what we're dealing with, a charged particle or atom, an ion. Sodium has 1 electron in that shell 3. Okay, that electron, excuse me, that electron is way away from the nucleus. It's out there all by itself. It's easy to wrench that electron away, and as a result, you end up with a charge. Okay, you've lost 1 negative charge. So the charge in the nucleus shows through as a +1. You've got 1 extra positive charge in that atom. Okay? So it's an ion. That's the ionic form of sodium. There are lots of atoms that have ionic forms. In fact, most of these elements to the left of this jagged red line, okay, most of these will have charged forms. In fact, I can't think of any that don't. Those are all metals, right? And metals are often charged. The things on the right of that line up until the second to last column typically don't have a full charge. They don't become ionic very easily. All right, so silicon, arsenic, tellurium, astatine, they don't really become ionic very easily. However, hydrogen, fluorine, chlorine, bromine, and iodine will become ionic fairly easily, interestingly. Okay. How does that happen? Come on. Here we go. All right, let's look at a simple example. We've got two elements in their elemental forms shown in this figure, plus what they combine to produce. On the left is the element sodium. That's a block of pure sodium metal. Right? Notice that the individual that's cutting it is wearing gloves. It's a good thing they are, because sodium reacts explosively with the moisture on your fingers. All right, so you don't want to touch it. In fact, when you have pure sodium metal, you have to keep it usually under nitrogen and in oil so that it doesn't react with anything. Otherwise, it'll react very, very quickly. All right, so that's sodium. On the right is chlorine. It's sort of a pungent greenish yellow gas. And yet, as you all probably remember from, good grief, grade school or junior high, atoms of these two elements combine to form a simple compound that we eat all the time and which is necessary for us, table salt. Okay? We have to have sodium and chlorine ions in our bodies. For example, sodium and chlorine ions are critically important in nervous system function. If you didn't have sodium and chlorine ions, your nervous system wouldn't be able to produce signals. Right? So how does this work? Well, to understand how this works, you're going to have to take a look at the electron configurations of chlorine and of sodium and ask, why is it that you can form ions with these two elements so easily? Right? Here's how it works. Sodium has a single electron, as you can see right here, okay, in shell 3. That lone electron, as I said, is easily stolen away from this atom. Chlorine is missing an electron to fill its shell. Okay? So that's a basic point that you should always think about when you're looking at how chemical bonds are going to form. Chemical bonds form to fill shells. Okay? Because full shells are more stable than unfull shells or unfilled shells. So chemical bonds will always form to fill up shells. All right, this works really well, because if sodium loses this electron, shell 3, it doesn't exist anymore because you don't have any electrons in it. It has a nice filled shell 2. Chlorine, when it gains this electron from sodium, has a filled shell as well. Okay, shell 3 is filled. The result of this is that with sodium losing an electron, a negative charge, it becomes plus charged. Chlorine gains that negative charge, so it becomes negatively charged on the whole. And of course, opposite charges attract. So they stick. Right? That's an ionic bond. Okay, it's formed when ions are produced of opposite charges that then stick together to form a compound. Okay, so sodium is highly reactive. It loses the electron, particularly to those with only one site left to fill. And with chlorine, it picks that up, becomes negatively charged, and these ions attract to each other, forming a salt. Right? This happens with every element in the same column as sodium and magnesium even. Okay? So we're looking at column 1 of the periodic table and column 2 of the periodic table. These are elements that easily form ionic bonds. Yes?
Why is it that chlorine becomes negative?
Why does chlorine become negative? The reason is because it's picking up one negative charge from an electron. Right? Remember, the electrons are negatively charged. And in that chlorine atom, as it stands on the left side, it's neutral. because the positive charges in the nucleus are exactly balanced by the negative charges outside. It's picked up one extra negative charge. Therefore, it's negative. Okay? Yes?
The sodium atom
Yes.
have 7 open shells or no?
Question is, does the sodium have 7 open spots in that third shell? No, it really doesn't. You shouldn't think of those as being sort of already there. If another electron was to come in here and get placed into sodium, it would get stuck in the appropriate spot by itself in that shell. But there's no spot that's sort of waiting there for it to come in. Okay, that's why I say when that lone electron in the third shell gets pulled off, it's as if shell 3 is not even there. Okay, that spot is not still there. It's just that that's where that electron has to go so it doesn't bump into all the others, basically. Okay? So if you remove it, then you don't even have a shell to worry about. Okay? It's not something that pre-exists. It's just a location, in a sense, an energy level at which you would find that electron.
But how come chlorine has an open spot right there?
Because it has the capacity to take on another electron in that shell. Right? There's not in a sense an open slot that's already waiting for an electron, but an electron could go into that shell if it became available.
Sodium.
What about sodium? Well, yeah, you could put another electron in there. I don't know how you do it. I don't know the high energy physics involved. But yes, theoretically, you could put another electron in there.
It can still hold 8,
Yeah, oh yeah, that third shell can still hold 8, yes. It fills up to 18, but we're not dealing with the 18. We're dealing with the first 8 because the next ones are weird and we don't want to mess with them. They fill in strangely. Okay? If you're really curious, what happens is you actually go to shell 4 and fill part of it first and then you go back to shell 3. Okay? That's why we don't want to mess with it. Like I say, take chemistry if you're curious about that. Okay, any other questions on that? Cool. Good. Okay, well, let's see if you got it. There's the question. Beryllium ions would associate with how many fluorines to produce the compound beryllium fluoride? It's a salt. Okay? What I suggest you do is figure out the electron configuration of beryllium, figure out the electron configuration of fluorine, and that will tell you the answer, basically. It'll also tell you how many bonds are going to form. Okay, well, let's just take a poll and see what you came up with. How many people say A? Okay, fair number. How many people say B? Okay. How many people say C? Okay. Any for D and E? Okay. How many people... Oh, I shouldn't ask that. I was going to ask how many people have no idea, but that's okay. You don't have to show your hands. Who knew that to you? All right, let's think about this. Beryllium has 4 electrons, right? All right, so you fill up shell 1, then you put 2 unpaired electrons in shell 2. Those two unpaired electrons are easily stolen. And not as easily as sodium with its one lone electron, but they're pretty easily stolen. And certainly with fluorine, they're going to react pretty violently. So you have two electrons that can be stolen. However, fluorine only has one slot available in each fluorine atom. Okay? So you're going to have to absorb, in a sense, those two electrons that are coming off of the beryllium. You're going to have two fluorine atoms to suck those up. So the result is you get two electrons, or two fluorine ions that are being used. Okay, so we form beryllium fluoride, BeF2. All right, notice how I've written this chemical formula here at the bottom. This chemical formula shows how many of each type of atom is present. And so BeF2, that means there's one beryllium and two fluorines. And it's a salt, just like table salt.
So is that lone electron that he stole that is just another atom shell?
Okay, the question is that lone electron just in the outermost shell? It's in the outermost shell of the fluorine atom. Yeah. Because remember, fluorine has all but one electron spot filled. All right, so you can steal an electron from beryllium to fill that one spot, but then you've got a lone electron in beryllium that gets stolen even more easily. So a second fluorine atom just comes in and picks that off. Yes?
So are you eliminating the whole third?
You're eliminating the whole second shell of beryllium. Yeah, absolutely.
It's always going to be eliminating that shell, the last shell?
It's all, yes, you're always going to be mucking with that outermost shell. Yes. Okay, we'll stop there, and next time we'll pick this up and look at the covalent bond.